to the Journey Chez Chem and another fun-filled day of chemistry. I know you're excited. I'm excited. Well, you need to please do the warm-up questions to the best of your ability, and we'll discuss them in a moment. In number 1, we're checking to see if we understand our periodic trends. Well, electron affinity. Electron affinity is the attraction an atom has for an electron. Well, when we look at these, we see that we have an S1, an S2, and an S2P1. And the S2 arrangement is the lowest energy, and therefore it's not attracted to another electron as much. And therefore the answer here would be my magnesium. The largest electronegativity, well, electronegativity is a man-made scale, and there are no exceptions. We're reviewing that idea as well. Oh, and I left off an element, and that would be sulfur here, and therefore sulfur is my answer. The largest ionization energy is the amount of energy that is required to remove the outermost electron. Well, when I look at these, I see I have a Ben exception. I have S2, the nitrogen is S2P3, and it goes 2 electrons in the S orbital and 3 electrons in the P orbital, versus oxygen, which is S2P4. I have my 2 electrons in the S orbital, and I have 4 in the P orbitals. And we recall that we have a school bus rule, Hund's rule, and we put 1 electron per orbital, and then we go back and fill. Well, this is much lower energy because they are rotating all in the same direction, and therefore it requires more energy to remove that electron than it does this one that it's a little bit unbalanced, and they're just fine with losing that one. And therefore nitrogen has the largest ionization energy. The lowest ionization energy, in general, the trend is that it does increase as it goes from left to right. And you'll recall that we sometimes think it goes 1, 2, 3, 4, 5, 6, 7, 8. But what happens here, because of the exceptions in ionization energy and electron affinity, we go 1, 3, 2, 4, 6, 5, 7, 8. And we have these 2 exceptions where the Ben columns are, the beryllium column and the nitrogen column. However, the trend is that it does increase as it goes from left to right. And we're looking for the lowest, and therefore sodium would be the least. For the size, we need to look at the snowman. And the snowman, he always has a little head and a big body. And he always falls over in this direction. And therefore the size increases as we go down because we have more and more energy levels. It decreases as we go across because we have more and more protons holding tightly onto those electrons, making the size smaller. We want the smallest size, and we always need to revisit what the question is actually asking. Well, we want the smallest size, and therefore when we look, we're going from left to right. Boron, carbon, nitrogen, oxygen, and fluorine. Not phosphorus, that should be fluorine. And the smallest size would be the fluorine. And fluorine is the smallest of that period. Then we want the largest size. And when I look here, I'm going down the column. Boron, aluminum, germanium, and indium. Well, its size increases as I go down, and therefore the largest size will be the indium. And that's how you do number 1. In number 2, we are asked 3 different questions. We're asked for the ending electron configuration, the oxidation number, and the number of valence electrons. Well, for the halogens, my ending electron configuration is S2P5. The oxidation number is -1, and it has 7 valence electrons. 2 plus 5 gives me 7. And the valence electrons are always only the S and the P as in Paul electrons, nothing else. The alkaline earth metals, they're in the ending electron configuration column of S2. Their charge is +2, or the oxidation number would be the same as the charge, +2, and they have 2 valence electrons. The noble gases have an ending electron configuration of S2p6. Their oxidation number is 0. They do not want to gain or lose electrons. They're a very stable electron configuration. And they have 8 valence electrons. And even though they're valence electrons, that's the full octet. And so they don't want to bond with anything. Chalcogens are the chalk formers, and their ending electron configuration is S2p4. Their oxidation number is -2, and they have 6 valence electrons. 2 + 4 gives me 6. Now at this point, I want to discuss a little bit about the characteristics of metals versus nonmetals. And first, let's discuss metals. Well, most of the elements on the periodic chart are metals. Let's take a look at a quick drawing of a periodic chart. It goes like this. And we have a diagonal line that we made heavy, heavy, heavy here between the metals and the nonmetals. So there are many, many more metals than nonmetals. However, hydrogen here is a nonmetal. It's placed here because normally its oxidation number is +1, and therefore it is put in this column with the metals. But we know that it is an exception, although we do have many more metals. So let's talk about their characteristics. Well, metals tend to want to lose electrons. They're unstable. And they are ductile, which means they can be pulled into fine wires, like copper wiring in our homes. They are malleable, which means we can hammer them into thin sheets, like tin roofs. Or even sometimes siding, metal sidings. They are good conductors of heat and electricity. You could be laying out in the sun and have a chain on, and suddenly it gets very, very hot because it's conducting all that heat from the sun. That's some of the characteristics of metals. Nonmetals, on the other hand, want to gain electrons. They are poor conductors, meaning that they're insulators. They're good insulators. They are often brittle solids or gases. And that's about all I have for the nonmetals. There's not as many characteristics of nonmetals as there are metals. But the very important part is that nonmetals want to gain electrons, and therefore they're more stable. Well, that's what we had for today, a little bit every day. And it was some fun, and thanks for being here with me, and I can't wait to see you tomorrow. Bye.